And the next presentation will be given by Professor Ullrich Pfeiffer from University of Wuppertal, Germany.
Thank you very much. So welcome everybody. My name is Ullrich Pfeiffer. I'm with the University of Wuppertal in Germany, and I'm going to talk about radio front ends for 100 gigabits per second and beyond. And as you see in the title, I haven't dared to put 6G down somehow, and I'll leave it kind of up to you guys and to the discussion later on if you want to call it 6G or maybe 7G. So, you know, I'm more of a hardware person, and I would like to give you a little bit of perspective from a hardware guy, and I'd like to give you some performance metrics to see where we are at the moment and where things are going to. As a hardware guy or a circuit designer perspective, we as a circuit guy, we are following basically the pursuit to unlimited bandwidth. Yeah? So we started out in the microwave range, moved up in the millimeter wave range, and then into the sub-millimeter wave range. That's the next thing. Many people talk about the terahertz range when it comes to sub-millimeter waves. And as you see, there are different kind of communities that are addressing this frequency band. You know, the green part here is addressed by the photonics community for a very, very long time. And we are kind of new to this field as an electronic engineer. So this is the red part, which I think is something that can be addressed easily with the current state-of-the-art silicon technologies. And this is something we need to talk a little bit about, because many of the applications that we are talking about here require economies of scale. We really have to bring down the cost, and silicon technologies are really a key enabler for this application in the future. So now let's look into the applications that we could address with silicon. And in the past, the photonic people really have done a lot of imaging at these high frequencies before, but slowly you see also silicon technologies that move into this domain. And we have seen even terahertz cameras implemented in standard CMOS technologies that are USB operated, very low power. They can be hooked up to automation robots, and you have seen handheld sources which run from a 1.5 volt battery. So things can be done, and of course there are also many other high volume applications that slowly move in. Automotive radar, of course, moves up the frequency ladder the same way as many other applications, and ultimately, of course, the communication has the high volumes that people that are designing silicon circuits are looking for. And just recently, last year, there also has opened up an IEEE standard, the 802.15.3D 2017, which opens up the frequency band from 252 to 322 gigahertz for communication applications. Now, the question though is, can we implement something in silicon? So can we design a terahertz radio front end? Now, when you think about implementing this in silicon, of course, you may wonder about the technology that's available. And let's look into the most advanced and fastest technologies that we have today, and this is a silicon germanium bipolar technology. And when you look back 10 years where we started at, we had cutoff frequencies, which means the Fmax, the maximum frequency of oscillation of a silicon transistor, at the order of about 200 gigahertz. Now that has gone through a number of technology improvement cycles. We went up to 500 gigahertz in 2010, and even now we moved up to 700 gigahertz. So the performance of those transistors has increased substantially, and that opens up a lot of new applications in communication and also moves us, of course, in this domain towards 6G and beyond. Now, the question though is, can we implement a generic communication transceiver? And this is shown here, something like a double balanced Gilbert cell up conversion or down conversion mixer. Of course, when you are talking about this very large bandwidth, then one of the approaches is that you're trying to get away with very low spectral efficiency and really try to leverage the large bandwidth that's available at these high frequencies. And then you start wondering about what kind of link budget do I actually have when I go into this. And you will very quickly figure out that it is kind of challenging because when you even assume some of the more conventional achievable parameters here, like output power on the order of 6 dBm, maybe noise figure of 10 dB, you will very quickly see that there's something missing, because if you don't have any antenna gain on your transmitters and receivers, you really end up in a very, very small range. And only with antenna gain, really, you can get up to something that's useful in the order of meters that we are talking about when we try to do communication. And all that needs to be trade off against each other. So the circuit design challenge here really is to find the optimum between these different kind of parameters. And antenna gain and packaging is one of the key things that we have to address in the future. Now, this is what we had in mind. So then we started off looking into some of the architectural design trade-offs here. And there's a transmitter block diagram here on the top, as you see. And there are two receivers that I would like to show you and discuss a little bit the various kind of trade-offs that you have. Now, we don't have to go really into details of how these block diagrams work out. Maybe one of the important things, though, to mention is that this is a tunable LO, so you can change the reference frequency to address different kind of carriers from 220 to 260 gigahertz. That, of course, is not the RF bandwidth. The RF bandwidth is smaller than this. It's just the LO reference. And then the other thing that you may notice is that there are antennas now in these block diagrams. Maybe at lower frequencies you have not seen this as part of the transceivers, but the wavelengths get small enough so that you can finally integrate the antennas also on the silicon chip. And if you look into the actual die micrographs, you see them here. You see that the antenna here is on the right side, for instance, on the transmitter on the top, and you see the two receivers left and right that I would like to talk about. And you see the LO generation part is actually pretty large, so a lot of area is required on the chips to actually get up to these signals. So higher frequencies are not very efficient to generate, and therefore you need not only a lot of DC power, you also need a lot of area on a silicon chip to implement that function. The other thing you see is that packaging is getting important, as I mentioned, and you need to get up to the very high directivity antennas. And the on-chip antennas itself, they're not directive enough, so you have to do something else. Either you would increase the aperture, which means you have to move to phased arrays, for instance, integrate tens or hundreds of antennas, or you can use a silicon lens. And this is what we've done here. So you see, we actually have glued the chip to a silicon lens. And this way, the on-chip antenna is kind of the primary feed of the antenna, whereas the lens is the secondary antenna. And that gives you a very good directivity of 26 dBi. And this is really important to understand that this is required to really bridge some distance. And here you see some of the prototype modules where you see the silicon lens. You can also cool this and use pretty standard FR4 technology. So except for the lens, there's really only silicon here involved and low-cost FR4. Now let's look into some of the measured results. And this is, of course, important to see if we can get the performance done. And here you see the transmitter RF bandwidth for different kind of IF drive powers. Of course, you can saturate this. And an important number here is, of course, output power that you would like to figure out. And this is actually radiated power, so you can get very close to 10 milliwatts. 10 dBm is something that you can generate these days in a silicon process. The LO is tunable, 220 to 260 gigahertz. And then, of course, what really is, of course, of interest is the RF bandwidth. And you can get something like a 3 dB RF bandwidth of 25 gigahertz. That's a pretty large bandwidth. And the question is, how do we leverage this? And if you look into the receivers, I was presenting you two versions here. One that has an amplifier right after the antenna, and on the right side, we omitted the amplifier, and we go directly into the receiver mixer. And you see, although you cover kind of a similar kind of carrier frequency, you see that the RF bandwidth, when you look at it, is a bit smaller here in the amplifier one, because many of these amplifiers, they are highly tuned, and they limited the bandwidth. Whereas on the right side, this implementation here has a little bit larger bandwidth, up to 28 gigahertz. And if you mix this down, you get an IF bandwidth here of 14 gigahertz. Now, the other thing, of course, is when you omit the amplifier, of course, you have a higher noise figure. You see this here. The noise figure here is slightly higher than on this version. Here you can get down below 10 dB. Here you are above 13 dB. No? So the question is this noise figure really the only measure that we have to judge the performance of those circuits? And we will see it's not, because there are many other impairments of these links that matter. So let's look first into a short demonstration how that looks like. So you have these boards mounted here on a rail, transmitter here, receiver there, and you can directly take an antenna signal, let's say a DVB-T signal from an antenna and send it in as an IF signal. Because it's so wideband, you can directly go through your transceivers and then hook it up to a TV to demonstrate that it works. And if you put in your hands, of course, you're going to block the signal. You can also go through cardboards. That's a very interesting demonstration of terahertz radiation, that it is not actually reflected from dry materials or absorbed from dry materials. All right, but of course you would like to demonstrate data rates, so we have to move on to something that's more a type of a test equipment, and you need real-time, very fast oscilloscopes and arbitrary waveform generators, which is shown here in a demo setup. And that, of course, pushes also the capability of the test equipment, because you have to feed very high data rate, complex modulated data into these transmitters, and then also have a real-time scope to sample that fast enough. So here we are hitting the limitations of the test equipment that's currently available. And when you look at the results here, first with the amplifier first receiver, you see some of the 16 QAM cancellations that we measured up to 90 gigabits. And here on the top right chart, of course, you see the EVM and respective bit error rates here over the LO reference or carrier frequency, and you see that that really is able to get up to very high data rates, up to 90 gigahertz per second. And of course, also interesting is how high we can get up to the right side here. In particular, if you would like to address this IEEE standard, there we would like to move close to the 300 gigahertz. So here you see another summary of the two implementations, mixer first, receiver here on the right side, and the amplifier first one. And because of the slightly larger and flatter bandwidth of the mixer first, actually in this implementation we were even able to get up to 100 gigabits per second with an EVM of 17%. So this is a pretty good number, although you may wonder about the range, and this is something we need to talk a little bit about. So this data was measured over 1 meter range. If you go further, you have to drop down in data rate. So at 1.8 meter already, you're down to 80 gigabits per second. Now, and the reason for this is, of course, that there are many other impairments of the hardware. So it's not only the SNR, the signal-to-noise ratio, that you have. You also have to worry about the spurious free dynamic range. You need very clean LO signals. Also, you need to make sure that on the receiver side, you have a good LO to IF isolation, and that as soon as you make your IF bandwidth wide enough, then you're really running into these impairments, these unwanted signals here into the right side, and that's the reason why you have to then at some point have to lower your data rate. And this is something that we are addressing, of course, in the circuit design, and this is also summarized here again. So as long as you stay below 50 gigabits per second, you're really only limited by phase noise and SNR, and as you increase your IF bandwidth, then you're running into these harmonics, and that then kind of raises the EVM, and therefore at some point limits the achievable data rates. And only here above 90 gigahertz really you have the external IF to baseband leakage, which is a problem. Now with this hardware, when you look at the channel allocations out of the IEEE standard that's available, you see these yellow parts. These are the bands that we finally can address with this chipset. So of course the bandwidth here is quite narrow, so we cannot get the 100 gigabits in this standard yet. But at lower frequencies, as you have seen, at 230 gigahertz, we have these 100 gigabits per second available over 1 meter. But when you look in the standard, the people are talking about much larger ranges. So the question is, what do you have to do to even go further than a meter? Because that's not enough for many of the applications that we have in mind. So you can go back to your link budget, basically, and see what would have to be done to go from the 26 dBi lens gain that we have to something like 50 dBi. And if you have that on the transmitter and receiver, of course, then from the link budget, you would be able to get to 100 meters with this. Then, of course, your lens needs to increase to something like 6.5 centimeters. So this is the aperture of what we are typically talking about when we talk about handheld devices now. So it is within range that we can get it, but it's a very directive beam, of course. That's why we need to look into beam steering capabilities of the hardware, that we are able to steer this very narrow beam over this large distance. Just for your reference, I've included here some of the state-of-the-art hardware implementations that we've seen on transceivers. And if you compare this technology here, this is done in a silicon germanium process, as I mentioned, with the existing implementations. You see that only 100 gigabits per second so far had to be done in an indium phosphate technology. So silicon there is creeping up in terms of performance and is an interesting option that in particular addresses these very high volumes that we are looking for commercial applications. Now this brings me to the summary of my talk. So you've seen there are plenty of opportunities, and in the past many of them were limited to imaging and sensing applications, whereas the communication now really is getting more and more attention. And you have seen that the hardware is able to give us something like 100 gigabits per second over a meter, or even up to 100 meters if you start adding extra antenna gain there. Future challenge, of course, is to improve the link performance. So there's plenty of stuff to do for us hardware engineers. And if you go beyond the RF front end, of course, there's a lot of stuff missing, and that's the baseband. No? So really on the baseband side, you have to have something that can actually handle these kind of large IF bandwidths, and this is an unsolved problem so far. We have not seen, beside this very expensive test equipment, that there's anything that can handle these kind of very large IF and RF bandwidths. Very important thing to remember. So this closes my presentation, and I hope we will be able to close the 6G gap and find the right applications that can actually drive our hardware here forward in frequency and to communication applications in the future. So that brings me to the end. I would just like to thank all my PhD students, of course, who have contributed to the work here, and some of the funding agencies as well. Thank you very much for your attention.
Questions from the audience? Yes.
This is way outside my experience horizon, but I wonder, there's been a lot of interest in visual light communication elsewhere, I haven't heard it mentioned here. How would you compare the trade-off between kind of your, because the ranges typically are not that different. I mean, you often get tens of meter type of ranges for visual light communication, sometimes more. And what do you see as the trade-off between these two approaches, the terahertz, multi-hundred gigahertz, and going all the way to visual?
Yeah. Well, there is, of course, one of the key arguments that I always try to bring up is the fact that we can integrate it in something that is compatible with conventional microelectronics. And if you are talking about photonic systems, of course, you always have to have something like some hybrid technology with some photonic-enabled systems. And this, so far as my experience is concerned, is not something that is really what we are looking for when it comes to implementing this together with something that is making it into a mobile device. So that's why I think this is really the only technology that has sufficient quality, performance, and that can be something that can be made small and integrated in the future. Yeah.
So what you foresee kind of as because we typically tend to believe that Moore's law is taking us to better and better all the time, and that's definitely not that easy to calculate in the RF and terahertz domain. So what do you expect about the future technologies in the 10-year time scale, and how much it is about the technology that improves, and what is actually the role that we are smarter and do it better in the system-wise? What's your view on that?
Yeah, most of that Moore's law, of course, was driven by making things smaller for the purpose of integrating more transistors. When it comes to RF performance, of course, you're not really driven by that need. You don't necessarily have to have more transistors in an amplifier. So we are, in the past, of course, when you look backwards, we were running kind of on this advantage that when you make things smaller, you also get better transistor performance. That was the case when you look back. But now it looks like when you go ahead and you make things smaller, you increase all the parasitic elements, resistances, capacitors as well, unfavorable in terms of the transistor performance. So it looks like that the Moore's law at least cannot be leveraged that well in the future as it has been in the past. So that's one of the reasons maybe why the RF performance of highly scaled CMOS technology is not improving as much as we may like. However, there is the silicon germanium technology, which is more like a vertical implementation and therefore can be better scaled. So some of the predictions are telling us that these technologies should be able to get even above 1 terahertz with their fmax. So I think there's a lot of headroom for silicon technologies to improve this further. It may not be CMOS for the very, very high frequencies, and this is a little bit counterintuitive when you compare this with the past, where always you've done something in a bipolar transistor and then you've done it in CMOS again, and because it was lower cost. That may change as we go forward, but still a silicon germanium bipolar transistor is also a silicon technology and benefits from the same kind of cost trade-offs that you have with CMOS as well. So I think this is still a very viable option for the future there.